In this video, we will look at what an active filter is. If you haven't viewed the video entitled Introduction to Filters, uh, watch that video first, and then this video builds upon that one. So here we have a single pole, that's just one pair of resistor and cap, a single pole filter. It is a low pass, meaning that low frequencies have an easy time passing through it. High frequencies will be attenuated. You can see that a couple ways, just by way of review. The voltage division that would occur would show us that at low frequencies, the impedance of the cap is very high, and there'll be all the voltage across the cap. But then as frequency increases, the capacitor's impedance decreases, and you would have less and less voltage across the capacitor, meaning less and less output voltage. Another simple way that you might find useful when you're looking at quickly identifying high pass, low pass, you can look at the capacitor and just recognize that at low frequencies it looks like an open, and at high frequencies, very high frequencies, it starts to get close to a short. And so what that means is high frequencies would be shunted or shorted out down to ground. And in fact, that is a naming convention for this filter. You could describe it as a single pole, low pass shunt design, because the filtering action is happening by way of a shunt path that the capacitor provides for high frequencies. So they won't get through, they'll get shorted out, the high frequencies will, while low frequencies continue through. So we have our filter, and to turn it into an active filter, we simply add an op amp. So here we have a simple addition of a voltage follower, also known as a buffer, and nothing changes as far as the input to the output signal will be the same. It'll still be a single pole, low pass filter, although it would now be recognized as what we call an active filter. And probably the naming convention active filter comes from the fact that we now have some active circuitry here that brings some additional capability to the filter. With just the pole by itself, we have maybe potential problems with loading. Anything you connect to the filter at this point, you can see actually creates a series parallel circuit. So you have a loaded voltage divider now, and that can interfere with the original intent of the low pass design. As we looked at in the introduction to filters, this voltage division we looked at purely in terms of these two components. And the fact is, as soon as you connect a filter known as a passive filter, as soon as you connect it to anything, that thing becomes a load that sits in parallel here. And so you have a series parallel circuit, or otherwise a loaded voltage divider, we would call that way back in the DC course. So that loading effect can be remedied. It can be totally done away with by adding the active circuitry that an op amp brings to the table. And you can see a simple buffer, we could call this, or a voltage divider, a voltage follower rather. It now will take this output of the passive of the filter of the pole and bring it right to the output here, but without any significant loading effects, because the input impedance of an op amp is very high, so it doesn't present very much of a load at all to the filter itself. So it's now called an active filter. It has active circuitry in here that can buffer the output. In other words, you can now present a load here that maybe does pull current or does present a significant load here, but the filter here will not be subjected to that. It will not see that because the buffer sits between them. And the filter is better left alone, not to have to provide any kind of a load current, which would interfere with its voltage division. So that's why we call this a buffer, a voltage follower. But it does a nice job sitting between your output and your filter, and the filter stays untouched. It remains essentially a non-loaded voltage divider to do its thing, regardless of what you hook up over here. And the other thing that this active circuitry, the op amp, does is provide the possibility of gain. So we get that added feature also. Um, Here we just have it wired as a simple buffer, voltage follower, to eliminate the loading effects that we would otherwise get presented to the voltage divider here. That's our filter. But if we want to, we can play around with RF and RI, and we can have a variable gain filter. So then we have the filtering effects, and those are buffered. That's the first thing the op amp brings to the table, the ability to buffer and prevent loading effects on the filter. And then the second thing it does is present the option for adding gain to the filter. So we now have a low pass filter that we could put any gain we want along with it. One other thing I did want to mention about this type of a circuit, where it's essentially a buffered voltage divider. Speaking of creating the voltage follower, the buffer, if you recall back to our introduction to op amps, a single resistor can also be used here to bring back the full amount of output back to the inverting input, and then hold the gain at just one, essentially no gain, right? Um, just unity gain, just one. So uh, let's do that. I want to show you something because you will run into this, when you crack open a book on filters, and I don't want you to be puzzled by what you see here. This is oftentimes done. You might use you might see a resistor being used, and it's not going to really change anything as far as the gain. If you do a straight connection from here to here, you have a gain of 1 or a buffer. If you use a 10K resistor, you'll also have a gain of 1. You can see there's no voltage division with Ri to reduce the amount that's brought back as far as negative feedback. But I want to bring this up again. I want to show you this because this is oftentimes done. And honestly, I can't speak to maybe all of the details as to why. I suspect if you see this, many times what I've seen is it's matching the resistance that's used in the actual pole. So I brought these values in from our introduction to filters video. We used, if you recall, we used a 10K and a 0.01 microfarad. And I've seen in many books on filters, I've seen this done. And I would, like I say, I'm not an expert on that. I would suspect there's some benefits maybe as to symmetry, or maybe avoiding offsets, maybe reducing currents. If you think about it, that might all be sort of in the mix. But with my limited understanding of why that's there, I think it's fair enough to say, it kind of makes sense from a symmetrical point of view, perhaps. and leave it at that. And you can dig up some info on that if you want. You can find whole books on active filter design, and I'm sure find the answers in great depth as to some of the more deeper concepts. For us, for now, let's just stick with the fact that you will run into that, but don't mistake seeing a resistor in the feedback path for anything other than a simple buffer still occurring. And in fact, like I said, I've seen them kind of match. If that's a truism, I'm not totally sure, but it kind of makes sense to me. So, okay, so that was kind of a long speech on just knowing how to recognize that and not be thrown for a loop when you see that. And of course, like we said, with the addition of an op amp, you have the option to add gain to your filter, and that would just be, if I can squeeze it in here, you could add some amount of a resistor for RI. So if I wanted this filter to have a gain of 2, right? Done. Maybe I'd like it, it's not a decimal. Maybe I'd like it to have a gain of 10, you know? So there you go. So now I have an active filter with a gain of 10. I have a low pass, single pole, shunt design, active filter with a gain of 10. Of course, this could be, I think we were using 100K there in our last exercises. It could be like this too. There's still a gain of 10, right? Yeah, 100K and 10K. And if we wanted to make the gain variable, there you go. If that's readable. Clean that up a little bit. So there I cleaned it up a little bit, just trying to show you though that you can have the variable gain added to the low pass filter, and now you can adjust the amount of low frequency that you have here. You kind of, be like a tone control or an equalizer of sorts. And it could be, for example, well, we probably changed some values here. If you remember from the other video, I think we were at like 1.59 kilohertz for our cutoff frequency. So 1.59 kilohertz, we could change that to by a factor of 10. There you go. That's 159 hertz cutoff frequency. Now it's looking very much like a bass tone control, or a band on an equalizer that would control this low range. How much bass did you want? Booster cut here to get however much bass at the output that you want. Just a quick, simple example. And I just caught myself. I think I've been saying that we have a gain of 10 in our example. Has that been bugging you this whole time? So I'm losing points on a test there, right? My input is over here. It's coming in on my non-inverting input. Remember, we said try to use that as a memory aid, and so I have to add 1. So back up wherever I started saying, that we have an example circuit with a gain of 10, that would be a gain of 11. So that's easy to forget. And here in this example, we have a possibility for a maximum gain of 11. We have our 100K pot being used as a variable resistor. So it could vary up to a gain of 11. And once again, we have that same example of electronics where each little thing that we learn maybe isn't difficult in its own right, but the trick is definitely remembering each little thing. So let me reset this circuit back to what we were familiar with. We'll just have our fixed 100K here as an example. 10K, there we go. And I want to show you another way that this same circuit is drawn, once again, if you crack open a book on filters, I don't want you to be thrown by what you see. Um, and our book has this convention as well. There seems to be a conventional way to draw this same circuit, and it is the same circuit. So let me sketch that up for you, so that it'll be something you don't have to stare at and think it's a different animal when you look at it in a context of a chapter on filters or a whole book on filters. So I'll sketch that here. So here it is. This is the way active filters are oftentimes drawn. Take a minute to look at the two circuits. They are the same circuit. I didn't put values in here. I wanted to show one more thing. Um, they flipped the positioning here of the inputs, and so on. And they're calling the feedback resistor RF1. So formally we knew this as just RF, and RF2 we knew that as RI. Right? And in the above example, of course, this is our 100K and this is our 10K. So I mean, just a little bit different naming conventions here. Um, Again, the point of introducing this is so that you don't think this is a whole different thing. Um, Here's our pole, our low pass shunt design filter coming into the non-inverting input just as it is up here. Then we've got a voltage divider that controls how much negative feedback is given to the amp as you bring the output back um, to the inverting input. Same idea. And in fact, in some ways, I forgot to add the output, didn't I? Your output's right here, just like it was. Squeeze that in there. So there's your output. In some ways, I even like this way of drawing it. I even like it better. It really emphasizes what we talked about when we introduced op amps as the negative feedback amplifiers that we looked at. When we first introduced them, we said we're using a voltage divider to take a certain amount of the output and feed it back to the inverting input. And that's how we were controlling gain. And you know, this method of drawing that voltage divider is I think is very apparent that that's what's happening. Maybe even more so than up here. So I mean, it's a convention that you'll probably see if you crack open a book on active filters. Just know it's the same thing. It's a non-inverting amp using negative feedback. But like I said, I even in some ways I like that. I like that obvious voltage divider showing up that way on a schematic. And the formulas we used before are still valid. They're the same ones we would use for these circuits. The cutoff frequency is still 1 over 2 pi RC, RNC here and here and here. That's our pole for our single pole filter. Gain, just like we did with negative feedback amplifiers, with RF and RI plus 1 in this configuration. Of course, their new names might be RF1 and RF2, but you can just remember this and just, I think, visually see where they belong. And of course, you have the option of creating a buffer with just a gain of 1, essentially no gain, by not using a voltage divider, but just either a straight connection or maybe a resistor by itself. So all those formulas are still the same. Nothing changes there. We've just added an op amp, and that's all. So once again, a very simple sort of introduction uh, for active filters. Just kept it with one example. Tried not to put too much out there all at once. Obviously, you can see, I think, if you reverse these positions here, you could have a quick high pass filter. Um, and what we've shown in this video, it is just the beginnings. It is just to get your footing, and then off you go. There are, like I say, whole books on active filters and different designs. This would be the simplest design, of course, where you just have sort of a single pole, sort of doing its voltage divider thing. But there's all kinds of creative ways people have found uh, to build poles around an op amp. So some of them easy to see right away, some of them maybe not so easy to see what's going on. But putting poles and op amps together to create active filters um, can get very creative. So chapter 23 actually is really well written. It goes through um, some more examples of some more complex designs. You start adding a second pole, for example. That just helps with what's called the roll-off rate. In other words, um, you know, if it is a low-pass filter, uh, when you when you're increasing frequencies, how quickly does the higher frequencies, how quickly do they fall off? You know, so that'd be known as the roll-off rate. But we don't have to get into all the terminology right now. That is this is as far as we need to go for our intro. But like I say, if this makes sense to you and you are curious and want to get more details, uh, chapter 3 is where you'll find them. And I think you'll find that the reading there is is actually quite doable. It's a really well written chapter, um, so I don't think it should be frustrating reading. You can just if you find the time or you're inclined to dig in a little more to all the other ways you can make a filter, there's a lot to look at and experiment with in that chapter. And I guess I could mention for any of you watching this video, even anywhere out there in internet land, the textbook that we use or that we're using is called Electronics Technology Fundamentals. Um, we use the conventional flow version. It's the it's by Robert Painter and BJ Toby Boydell. So if you were interested, and the chapter I referred to was chapter 23 to take you farther in this topic. Painter is spelled Payynter, and Boydell is spelled Boyder.